Hello, welcome to your MCAT channel session on light and optics. My name is Nzinga Mack, and I am a Kaplan MCAT instructor who's a huge fan of light and optics. It's definitely one of my favorite topics. So we're going to go into some of the details about what the MCAT is going to expect you to know about these concepts when it comes to testing. So with that, let's take a look at making sure we know what we're going to talk about. So we're going to be taking a look at the different components of that electromagnetic spectrum, and then we're going to delve into the idea of visible light and what you need to know about visible light when it comes to testing. We'll also take a look at the idea of the ray diagram. So I know that ray diagrams can be very confusing for students, so we're going to kind of break them down and see what you should be getting out of them when it comes to testing. We're also going to be taking a look at the systems that are going to be exploring diffraction so that we can see how light is going to bend and how that is going to affect various aspects of light. So with that idea, let's dive right into it. So let's take a look at our learning goal number 1 that we're looking at. So if we're taking a look at the electromagnetic spectrum and the properties of visual light, here we have a nice example of this spectrum. So you can see that you have your X-rays, you have your gamma rays, you have your X-rays, your UV. In the middle, here we have this visible spectrum, and you can see that you're dealing with your Roy G. Biv as the visible spectrum. So one of the things that you'll note is that as we're going from left to right, we're talking about increasing in the wavelength. So increasing in the spaces in between each one of these wave crests. But then as we're going from left to right, we're also talking about decreasing frequency. And you know what? That makes sense. If you have more space in between the individual wave crests, then we definitely know that you are going to have less of a frequency of the amount of waves that you're going to be getting per second. Okay, so that's going to be something that's important for you to understand. So let's kind of delve into this a little bit more deeply when it comes to this idea. I like that, Sonali. Real men in violet underwear are extremely gorgeous. That is amazing. Okay, so that will help you remember what's going to be the order in terms of your frequency and of your wavelength. Okay, so as we talked about, decreasing frequency, increasing wavelength. So if you think about those really, really big waves, it's going to take them so long for that huge wave to go by that they won't go by with as much frequency as the ones that are really, really short, and they're going to be really, really powerful. And keep in mind that the shorter the wavelength, the more waves that you get per second, the greater the frequency. So the greater the frequency, we know that the more powerful that wave is going to be. So if we think about those gamma rays and the X-rays, that's one of the reasons why they have the ability to do so much damage to our organs, because they're greater frequency, more power that comes along with these waves. Okay, so if you think about that idea, let's kind of look at some of the extrapolations. So you have your gamma rays, your X-rays, your UV, your IR, your microwaves, and then you have your big, huge radio waves. So I always like to imagine all the various types of waves that are going to be circling around me at any given point in time. So the radio waves that are going through the air, but I don't have the antenna that can pick them up. Then the microwaves, someone is going to be using a microwave, that's going to be emitting some of the waves. The infrared that we have, our UV, the visible, the X-rays. Hopefully there aren't too many X-rays running around or too many gamma rays, or if we know that we do have some background but not high enough to cause any damage. But if you think about that, there are all of these waves that are going to be interfering with the air particles that are all around you. So good things for you to kind of visualize what's going on. So if we go into a little bit more detail about our visible light, we say to ourselves, well, if we're thinking about that idea and we're thinking about real men in, okay, let's see here. Real men, so real men in violet underwear are extremely gorgeous. Then we can think about starting from this side and going to that side. So we think about all of these ideas. We also want to think of it in terms of how it relates to our speed. So we have c is going to be equal to the frequency times the wavelength. And by the way, when it comes to the speed of light, that's something that the MCAT wants you to memorize. So you tell me, what's the speed of light? Excellent, okay. So it's going to be 3 times 10 to the 8 meters per second is going to be the speed of light. So if we think about that as we go from our Roy G. Biv, except backwards, then we definitely do know that we're going to have that decreasing frequency and that increasing wavelength that we're going to be thinking about, okay? So if we think about that particular idea, we definitely want to note what we're going to be dealing with here. So we can see here we have our orange, we have our yellow, we have our red, and we know that we're going to be having all the various colors that you have in this particular spectrum, okay, for the Roy G. Biv that you're going to be looking at. So if we take a look at this idea, you know what? Go ahead and take a moment and do this question, and then we'll make sure that you come up with the correct answer. So we'll pull up a poll for you. So do this question and then give me a thumbs up when you're done. Okay, so I see that you're starting to get done with this question. Ooh, and you're in fans of D, which I like a lot. So let's see exactly how you can get to this D. So we said that, you know what, blue light is the problem, okay? So we wanted to figure out which is the least effective in supplementing this treatment of insomnia. So we said, okay, well, we need to figure out, when we assess the answer choices and we see that they're all talking about frequency, we need to figure out exactly what's going on when it comes to frequency. So we say, okay, well, we have to make sure that we know the wavelengths of the light that we're talking about. So when it comes to blue light, can you tell me what's going to be the wavelength for blue light? And by the way, this is something that you want to memorize when it comes to test day, so that that can really, really help you out with these types of questions. Nice, Brandon. Wonderful. Good. Okay, so it's going to be your 400 nanometers is what we're looking at. So we say, okay, well, we know the speed of light, 3 times 10 to the 8 meters per second, and we need to figure out the frequency because the answers are talking about frequency. So of course we want to make sure that we put that in terms of our standard scientific notation. And by the way, you can always take screenshots. So don't worry about trying to jot everything down. Just go ahead and grab a screenshot whenever you can. Print screen if you're on a PC, or you can use that Windows snipping tool, or if you're on a Mac, you can do your Shift Command 4, which is actually better than your Shift Command 3. Okay, so we look at this and we say, well, we just plug and chug. So we have our speed of light divided by our wavelength of the light, and we end up with our frequency. So one of the things that you can do is you can kind of take a look at the answer choices. So you want to note the exponents. So you see they're 13 and 14, so we're like, fine, we're not going to play with them as much. And then, but you can also take a look at the mantisses to see that some of them are different and some of them are the same. So you look at this and you say, okay, so it's approximately 3 divided by 4. So if it's going to be approximately 3 divided by 4, what should our answer choice kind of, well, let's do it this way. Which 2 answer choices can you eliminate if you know that the mantissa should be approximately 3 divided by 4? It's all about being lazy when it comes to test day. We want to do the least amount of work possible. Excellent. Okay, so you're like, B and C, we don't want anything to do with you, go out the window. Because we should know that it should be a little bit less than 0.75, because 3 divided by 4 is 0.75, so we should have something a little bit less than 7 in our mantisses. That's why B and C are going to go out the window. Okay, so then all it comes down to is now the exponent, and our correct answer choice is indeed going to be our D. Light emitting an average frequency of 6.3 times 10 to the 14 meters per second is what we're going to be looking at. Okay, so yeah, we're not fans. If we don't have to do math, then we're absolutely not going to do it. And if you want to take a screenshot of this now would be a wonderful time for you to take a screenshot of this. Okay. So with that, let's take a look at our second learning goal so that we can get into making sure that we understand what's going on with these diagrams. And by the way, one of the things that you'll note here is that we have that blue light has a wavelength of 400 to 500 nanometers. So we just kind of picked a value in the middle. So we said, well, let's do approximately 450 nanometers. So this isn't subtraction. It has a wavelength of 400 to 500 nanometers. And we picked 450 as a nice average that we're going to be looking at. Okay, and if you have other ways of dealing with this question, definitely go ahead and do it. The more critical thinking that you can do in order to avoid doing any type of math, definitely going to be a great thing for you to do for test day. Okay, so now let's get into the idea of the diagrams and what you need to know about these ray diagrams, which are my favorite because you can actually see this in action if you sit around and play with light like I may or may not do. Okay, so if we think about this, we want to think about what all of this is going to mean. But before we get into greater detail, we're going to be taking a look at the idea of here we have an approaching light ray. Let's say that we have some total reflection. So we know that the angle of incidence, and keep in mind that the angle of incidence is always going to be relative to the perpendicular to the object that the light is going to be entering. Okay, so if we take a look at this idea, here we have the perpendicular to the object that the light is going to be entering, and we're measuring the angle from that particular perpendicular. Okay, so over here we have the angle of incidence in which the light is going to be hitting. And that's going to be the normal, that perpendicular that we're dealing with. Whenever we have 100% pure reflection, what's going to be true about the angle of incidence as relative to that second angle? Good. Excellent. Okay, so we definitely do know that they're going to be the exact same. Okay, so the angle of incidence that we have here and the reflection, they're going to bounce off at the exact same angle. Okay, so good. So now let's kind of take a look at the idea of how we can delve into your various types of concave and your various types of convex mirrors that you need to know about when it comes to test day. So when theta 1 is equal to theta 2, classic reflection is what you're dealing with. Okay, so if we think about our spherical mirrors, we take a look at them and we say, okay, well, based on this idea, I want you to kind of imagine that this spherical mirror is going to be one huge circle. Okay, so this is going to be a huge circle, and this C that we have here is the center. Actually, you know what? Let me draw that a little bit differently so that you can have that C as the center. Okay, so right here we have that huge circle. And you're going to pretend, for the sake of this lesson, that that C is dead in the center of the circle, because that's what the C is going to stand for, the center of the circle. Okay, so if you look at it, the focal point is going to be exactly half of the radius. Okay, so focal points are specific mathematical phenomena. That's going to be half of the radius that we have. Okay, so we think about this idea, and that F value that we have is going to tell us, well, what's the difference, or rather, what's the distance from the mirror to that F? What's that distance from the mirror to exactly half of the radius is going to be your F value. Okay, so then if you take a look at your R, you say, okay, well, this is going to be the radius. So you don't often use the R value in a lot of these equations, but we're just kind of showing you what everything is going to be representative of. Okay, so let's say that we have an object right here. So if you'll note, here we have this object that is going to be behind the focal point. Okay, the object is going to be behind the focal point. Now, one of the things that I want you to note is that when it comes to the ideas of what these values are literally distances. Okay, so the little f is going to be, well, how many centimeters or how many millimeters is it from the mirror to this focal point? This value of r is going to be how many centimeters is it going to be from this mirror to the center point that we have here. And then when it comes to o, what that value of o is going to be is what's going to be the distance from this particular mirror to this particular object along that central axis. And what we have right here is going to be the central axis that we're going to be looking at. Okay, so whenever we say central axis, that's what we have right here in the middle. Okay, so good deal. So now you know what all of those values are going to stand for. So it's literally the distance from the mirror to those particular spots. So now, if we figure out where the image is going to be, we say, okay, well, in this case, the image is going to be over here. So this little I is going to be the distance in centimeters or millimeters or whatever from the mirror itself to the image that we have right here. Okay, and this is definitely going to be a concave mirror because you can see we're looking into the cave. So the light ray is going into the cave, so classic concave mirror that we're dealing with. And like Sonali is saying, with our concave mirrors, we have the light rays that are going to be converging. Okay, so I want you to remember that when it comes to testing. So if we think about this idea, we can come up with an equation. So your focal length is going to be equal to 1 over f is equal to 1 over O plus 1 over I, which is going to be equal to 2 divided by R. And a lot of times what the MCAT is going to do is that it's going to give you everything except for one of these variables, and it's going to ask you to figure out what the missing variable is going to be. So you're going to have to use your knowledge of fractions in order to attack these questions. Okay, so let's take a look at light when it comes to the perspective of your mirrors. So when it comes to mirrors, you want, if you're taking a look at how the light is going to be bouncing off the mirror, so the incoming light that's coming off of this object, it's going to hit the object and it's going to bounce off of the mirror. And we want it to bounce off the mirror and end up on the same side as the mirror. So we don't want the light that's bouncing off of my face as I'm looking into the mirror to converge behind the mirror. Because if I opened up my bathroom mirror case and then I looked behind the mirror and I saw an image of myself, I'd be really freaked out. So we want the light rays to converge back on the same side of the mirror when it comes to mirrors. I'd be like, I don't know what kind of horror movie this is, but I am not a fan, and no, okay? So with that idea, we know that on the same side of the incoming light, that's going to be the positive focal point that we're going to be looking at. So for mirrors, same side of the incoming light, that's the positive focal point. If we have something that's on the opposite side of the incoming light, that's going to be the negative focal point that we're going to be looking at. Okay, so let's take a look at what we're dealing with. Here we have our equation for magnification. So for magnification, we have m is equal to your negative I over your O is what we're going to be looking at. Okay, magnification, negative I over O. And if you're giving these numbers, you can definitely easily calculate them. So now, let's kind of take a look at what we have here. So we're dealing with the idea of the concave mirror. Like we said, we're looking into the cave. When it comes to the diverging mirror, it's going to be convex. It's going to be going in the exact opposite direction than what we're going to be looking at. Okay. So now let's look at very specific situations. So whenever it comes to placing an object either directly on top of the focal point, in front of the focal point, so we consider it in front of the focal point as it relates to the mirror, or behind the focal point, we want to know what's going to happen to those rays of light. Where are they actually going to converge? And by the way, when we talk about real images, what we mean is that you actually have rays of light converging there. As opposed to virtual images, where your eye is just extrapolating, your eye is just thinking that you have rays of light converging there. So that's what we mean when we say that's the actual real world definition of real images versus your virtual images. Okay? If you think about this idea, we can think about it when it comes to lenses, which we'll talk about magnifying glasses a little bit later. Okay, so we think about this, and here we have this object that's going to be behind the focal point. And the value for O would be the distance from the mirror to this object that we have here. Okay, so we want to know a couple of things about our image that we're going to end up with. Can you tell me what's one thing that we need to know about our image in order to accurately describe it? I love it. We need to know whether it's upright or it's inverted. Good. So is it pointing straight up relative to the central axis? So the arrows, if it's going to be pointing straight up, then it's going to be upright. If the arrow is pointing straight down away from that central axis, then it's going to be inverted. Good. Okay. We want to know whether it's virtual or real. So for a mirror, if it's on the same side as the incoming light, because we want all of our light when it comes to mirrors to be on the same side of the mirror, not behind the mirror. Okay, if it's on the same side as the incoming light, then it's going to be real. And that's where our positive F is going to be. If it's on the other side, then that's going to be virtual, and that's where we'll have our negative F. Good, okay? So we need to know upright or inverted. That's going to be one of the things. We need to know whether it's going to be real or whether it's going to be virtual. Okay, so that's going to be one part of it. And we want to know whether it's magnified or what. So what's the other polar opposite of the image being magnified? Good. Okay, so we look at that and we want to know whether it's going to be magnified or whether or not it's going to be reduced. So I want you to think about that when it comes to all of these types of images that you're going to be thinking about. Okay, so upright or virtual, and you want to memorize what happens when you have an object at a particular position. Okay, so that's going to be something that we are going to be looking at. Okay, upright or inverted, magnified or reduced. And we have the idea of whether or not it's going to be real or virtual. Okay, so let's look at this. So let's start drawing some light rays. And this is definitely a portion where you can draw some screenshots. Okay, so if we look at this, we say, okay, so if we're thinking about this, let me go ahead and move this so that you can look at it. We want to think about the first ray that we're going to draw. So this first ray that we're going to draw, we're going to call it a parallel ray because it's going to go directly from the object to the mirror, and then it's going to come back through the focal point. Okay, so let's take a look at what we have. So directly to the mirror, come back through the focal point. Okay, so that's the parallel ray. So let's go ahead and let's draw a central ray. So the central ray is going to go from the object, it's going to go to the mirror, and then it's going to go back along that central axis. Okay, so from the tip of the object to the mirror, and then it's just going to reflect back on the opposite side of that central axis. And then we can see where these light rays are actually going to be converging. And that's going to let us know what our image is going to be. Okay, so we have an image here. So let's describe this image based upon what we talked about. So is this image going to be uprighted or inverted? Inverted, good. Okay, so the original object was pointing up from the central axis. This image is pointing down from the central axis, so it's going to be inverted. Okay, is this image magnified or reduced? Is it bigger than the original arrow, or is it smaller than the original arrow? It's going to be magnified, good. And is this image real or is it going to be virtual? Is it on the same side of the incoming light for this mirror, or is it on the opposite side of this incoming light? It's going to be an actual real image that we have here. Good. Okay. So I want you to remember that for test day. Now would be a good time to take a screenshot if you'd like. So for test day, I want you to remember, if you have an object behind the focal point, the image is going to be real, it's going to be inverted, and it's going to be magnified. And a great thing for you to remember is that all real images are going to be inverted. And you can kind of think of that when it comes to the real images that are going to be transposed onto your retina. So as we know, all the real images, how do they show up on our retina before our brain puts them right side up? So it's a real image, so is it going to be upright or is it going to be inverted? So since it's a real image, good. Okay, so all the light coming into our eyes is going to be blasted onto our retina. It's going to be inverted. And then our brain says, no, 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 wait a minute. Gravity is going that way. So since gravity is going that way, we need to turn this image the other way around. Okay, so that's going to be good. So yeah, that's a good question. Anywhere behind the focal point. As long as you're behind the focal point, real, inverted, magnified. Maybe we can come up with a acronym for that. So behind the rim. Okay, behind the focal point, rim. Real, inverted, magnified. Okay, so you know what we're going to talk about next. So if we take a look at an object that's going to be on top of the focal point. Okay, on top of the focal point, we can draw the same types of rays. So the parallel ray going directly to the mirror and then coming back through the focal point. And then we can also do the center ray. Okay, so what do we see here that we're going to be dealing with? So what's going to be happening? Where exactly are these rays going to be converging? If you look at them, we're like, okay, so if we go here and here and here, we say there is no converging. So remember that. Whenever you have the image directly on top of the focal point, you are going to get absolutely no image, okay? And you can actually kind of test that out a little bit. It's hard to see, but if you want to take a look at a spoon that we have, so if you have a metal spoon, you can actually play with this so that you can see that initially your image is going to be upside down like we saw when you were behind the focal point, and then as you move the spoon, your image is going to, you know what, we haven't gotten to that yet. Your image is going to disappear. You won't be able to see it. But when you get to the focal point, your image is going to disappear. So with that, remember, on top of the focal point, no image that is going to be produced. Okay? It's real at infinity. So what we technically say is that these lines converge at infinity. Okay? So on the other side of the solar system, past the Milky Way, at the Andromeda Galaxy, which is our next door neighbor, this is where this image is going to converge. But for all real purposes, on Earth, this image will never converge. Okay, on top of the focal point, no image. So we think about this and we say, okay, well, let's take a look at the idea of what happens when we have the object inside the focal point. Okay, so let's do the same thing. Let's come up with the same types of rays. So here we're going to have it parallel to, and then we go back through the focal point, and then we are going to have that central ray. Oh, okay. Where is this image going to be converging? Christopher, are you referring to a screenshot that you wanted of the previous picture? So if you look at this, okay, I'll go behind in just a moment, let you take a screenshot of it. Yeah, if you take a look at this, you can see that it's going to be converging behind the mirror, okay? So we're like, okay, well, let's describe this image. So if we're thinking about this image, give me one descriptor of this image. Real versus virtual, magnified versus reduced, upright versus inverted. So we have a debate between real and virtual. Everyone agrees upon magnified, and everyone agrees upon upright, which is good, okay? So we see that we're going to get a magnified image because it's bigger than the original object that we have here. We see that it's going to be upright because it's leading up from that central axis. Good. Now remember, this is a mirror. So for a mirror, that positive F on the same side of the incoming light, that's going to be real. That negative F on the opposite side of the mirror from the incoming light, that's going to be virtual. So if you'll note here, we have an image that's going to be virtual, it's going to be upright, and it is in fact going to be magnified in terms of what we're going to be able to take a look at, okay? Because here we have this that we have right here. You know what? Let me draw it so that it's going to be starting at the bottom. Starting at the bottom and making it directly to the top, okay? But you can definitely see that that image arrow is going to be larger, so that's how we know that it's going to be magnified. Okay, so remember that. So, object in front of the focal point, virtual, upright, magnified. So in front, maybe we can come up with an acronym for that. Move in front, MUV, move in front. Yeah, I like that. Okay, move in front. So, in front of the focal point, move in front. Magnified, it's going to be upright, and it's going to be virtual. Now, if we think about this idea, memorize that, because sometimes just knowing that is really going to help you answer questions without having to do a lot of calculations. Okay, so now let's take a look at a different type of mirror. So previously, you saw that this was going to be a concave mirror that we were looking at. What type of mirror are we dealing with in this case? It's going to be a classic convex mirror. Okay. So for the concave mirrors, we're thinking about these ray diagrams from the point of view of that positive focal point that's going to be on the left-hand side. But for the convex mirrors, we're thinking about these rays from the point of view of that negative F that's on the opposite side of the mirror, on the virtual side of the mirror that we're looking at. Okay. So in this case, instead of our light rays converging and coming together, we know that our light rays are going to be diverging in this case. Okay, so let's take a look at this object. And in this case, since our focal point is on the other side of the mirror, since our focal point is negative on the virtual side of the mirror, so you know what, let's just kind of indicate that. So negative focal point, opposite side of the incoming light. Okay, and here we have the positive, so this is what we're going to be focusing on. So you know we can extrapolate this side is the positive focal point, same side as the incoming light. Okay, so let's do our rays. Except we're going to send our ray to the negative focal point because this is a diverging convex mirror. Okay, so parallel ray, send it to that negative focal point that we have on this side. Okay, and then we can do that central ray going along that central axis. So we can extrapolate back. We say, well, you know what? If we extrapolate back, we can figure out what type of image that we're going to have. So if we think about this idea, we say, okay, let's see what we are going to be dealing with. And we can describe this image also. So give me one descriptor for this image. Magnified or reduced? Upright or inverted? Real or virtual? Excellent. Okay, so we know it's upright. It's going to be reduced. Good. And it is going to be virtual. Excellent. Okay, so that's going to be something that we're going to look at when it comes to making sure that we understand what's going on. Okay, so we look at that idea and we say, okay, so any image when it comes to diverging mirrors is going to have these characteristics, that it's in fact is going to be upright, it's going to be reduced, and it is in fact going to be minimized, that it is going to be virtual. And if you think about this, this is going to be a classic example of those security mirrors. So in convenience stores, I'm from New York, so convenience stores, little bodegas in the corner, they have tons and tons of these little security mirrors in the corners. So the security mirrors, you'll see that everything looks really, really, really tiny in the security mirrors because they're diverging mirrors. And you don't have light actually converging there, but your eye is extrapolating. Based upon the way that these light rays are going to be going, your eye is extrapolating where these light rays would hit together. Okay, so that's why it's virtual, because the light rays aren't actually coming together there. Now, this would be a great time for you to take a screenshot. if you want to. I do want to take this time to remind you that you absolutely do not need to draw out ray diagrams for your MCAT. That's just not something that you're going to need to do. But the reason that we do this here is to show you how we come up with the idea of what an object is going to do if it's in front of the focal point, if it's behind the focal point, or if it's on top of the focal point. Okay? So remember that when it comes to this idea. So if you're like, where are these lines going? I don't understand. It's okay. And also remember, you can also rewatch the session. You can, if you don't get everything here, that's absolutely fine if you don't get everything here. You can watch it as many times as you'd like in order to get everything that you need out of these sessions. And yes, Dorothy, yes, always memorize the conditions. Yes. So memorize that diverging, that when it comes to this convex mirror, you're always going to get a virtual, upright, and minimized image. And yes, they always behave the same way. Good. Okay. So with that, since we said memorizing the conditions, Dorothy, you kind of anticipated us. I like that. Since we said anticipate the conditions, if you have an object that you have between your C and your F that you're going to be dealing with, what type of image did we say that we're always going to end up with? Give them all three to me at the exact same time. Whether it's real or virtual, whether it's going to be upright or inverted, whether it's going to be magnified or reduced. Yeah, I like that. We said rim, okay? So we know it's going to be real, it's going to be inverted, and it's going to be magnified. Excellent job when it comes to that idea. So memorize, memorize, memorize. Real, it's going to be inverted, and it is going to be magnified. Good, okay? So if we have the object at F, remind me, what do we end up with? I like that, Kimmy. Yes, okay, no image on Earth. Maybe it's going to be converging somewhere in like the Andromeda galaxy. Good, okay. So now we have the object between F and the mirror. So the object is in front of the focal point. What type of image are we going to end up with? Move in front. Yes. Excellent. Okay, so we said it's going to be magnified. We said it's going to be upright. And we said that it's going to be virtual. Good. So memorize these conditions that you have here. Okay? Now, in this particular diagram, we have a concave mirror. But when it comes to a convex mirror, no matter where it is relative to that focal point, what type of image are we always going to get? Give them to me all three. And even if you already see your answer trees, go ahead and put in there anyway, because the more you participate, the more you're going to get out of this session. Excellent. Okay, it's going to be upright, it's going to be virtual, and it is going to be reduced or minimized. Excellent. Okay, so now you can take a screenshot. And give me a thumbs up when you're done taking a screenshot, and I'll know that we can move on. Okay, awesome. You know what? I did promise, was it this diagram that you wanted to see? That you wanted a screenshot of this one? Okay. So if you missed a screenshot of that particular diagram, you can definitely go ahead and take a moment and grab it for when you had the object on top of the focal point. Okay. So good deal there. So now we are going to turn our attention away from mirrors, and we're going to turn our attention to a question so that we can see how we can deal with this. So you know what? Go ahead and take a moment and see if you can answer this question using the equations that we had. So you know, we'll go ahead and we'll put the poll up, and give us a thumbs up when you're done answering this question. Let's take a look at what you're saying in this case. So I see that we have the answer choices are kind of split a little bit, okay? So if we look at this, all you had to do is just plug in your F and plug in your I and plug in your O. And when you did that, you got to the correct answer of negative 2.4 centimeters is what we're going to be looking at, okay? So one of the things that you could have done, if you take a look at a little bit of a cheat, one of the things that you say, okay, well, this is a diverging lens. So the focal length, should it be a negative focal length or should it be a positive focal length? It should be negative. There you go. Diverging lens always are going to be relating to that negative focal point. Good. So you should have said, okay, so now I can get rid of C and D. And if I don't have time to do the math, I'll go eeny, meeny, miny, mo between A and B. Okay, and you'll still be able to get to the correct answer. So remember that. And you can take a screenshot of this if you'd like. Okay. So with that idea, let's switch gears a little bit. So if we switch gears, let's take a look at the idea of diffraction that we're dealing with. So we say, okay, well here we have our light rays that are going to be bending. So if the light rays are going to be bending, we definitely do know that depending upon the material that they're going in, they're either going to bend towards the normal, this perpendicular line to the surface, or they're going to bend away from the normal. So if we're taking a look at water, it's kind of harder for the light rays to fight through water, so we know that they're going to be bending away from the normal once they get into air. Okay, so remember that. So if we take a look at our equation, we can say to ourselves, well, we have to take a look at our N1 Snell's law. N1 sine theta 1 is going to be equal to N1 sine N2. Sine theta 2 is what we're looking at. So excuse the typo. We'll actually go ahead and write it the correct way. So N1 sine theta is going to be equal to N2 sine theta 2. Okay? So that's going to be our real equation. So that's what we're going to be looking at. And a lot of times on the MCAT, what will happen is that you're going to be given 3 of them, and you're going to have to figure out what the 4th one is going to be. And it's just mathematics when it comes to that idea. Okay, so let's take a look at the idea of lenses. So if we're thinking about lenses, we're going to be looking at it from a slightly different perspective. So for mirrors, we want the light on the same side as the incoming light. We want the image on the same side as the incoming light. That's going to be a positive focal point. But for lenses, if you think about the lenses of glasses or the lenses of sunglasses, where do we want the light to go? Do we want the light to be on the same side as the incoming light or on the opposite side as the incoming light? Exactly. We want it to be on the opposite side of the incoming light. So for lenses, the opposite side of the incoming light, that's going to be the positive focal point. Okay, so opposite side of incoming light equal focal point. So it's easier to remember where you want the light to go. Mirror, we want the light to stay on the same side as the incoming light because we want the image in front of us, in front of the mirror. We don't want it behind the mirror. Just think of the scary bathroom. You open up the bathroom mirror door and you see an image behind it. No. Okay. But for a lens, you want the light to go to the opposite side. So this is going to be the positive side that we have right here, and this is going to be the negative F side when it comes to the lens. Okay. So if we think about this object, we're going to use some of the same basic ideas. So we say, okay, we're going to do parallel, and we're going to send it to that positive focal point. So we send it to that positive focal point that we have here, and then we're going to do the central one. So the central one, we want to know where it's actually going to converge, because once again, positive focal point always goes with the idea of converging of light. Negative focal point always goes with the idea of the diverging of this light. Oh, this should look familiar. So the object was behind the focal point. So behind the focal point, what always happens when we have an object behind a focal point, regardless of whether we're dealing with a mirror or a lens? It's going to be the same. So you already know what it is. Yes, this is definitely deja vu, like Sonali is indicating. There was a little acronym that we came up with. So we said behind the rim. Let's jot that down. So behind the rim. Okay, so he says it's going to be real, it's going to be inverted, and it is going to be magnified. And that's exactly what we see here. Okay, so remember that when it comes to testing. Real, inverted, and magnified, regardless of whether or not it's going to be a mirror or a lens. Okay, so you can take a screenshot of that if you'd like. So then you take a look at, what's coming next. So we already talked about behind the focal point. So the next thing that we're going to talk about is on top of the focal point. So where's the image going to be if it's going to be on top of the focal point? Mirror or lens, doesn't matter. Exactly, no image, at least not on Earth. Okay, so if you note that, if you put all these together, it's a lot easier to do. And just so that you note, here you have an equation for power. It's going to be equal to 1 over your F. Okay, so good deal there. Okay, top of the focal point, we draw the same diagrams. We're trying to figure out where they're going to converge. Where they're going to converge is never. So we know that we're going to end up with no image on top of the focal point. Okay, so the next thing that we're going to do is in front of the focal point. So remind me, what type of image are we going to end up with? Well, regardless of whether it's a mirror or a lens, if we put it in front of the focal point, move in front. Excellent. Okay, so you can take a screenshot of that if you'd like. So if we move it in front, then we say, oh, okay, well, we're going to end up with an image that's going to be magnified. We're going to end up with an image that's going to be upright, and it's going to be virtual. And by the way, that's exactly what a magnifying glass is doing. So here's the actual object that the magnifying glass is looking at. And then you say, well, the magnifying glass takes it, and our eyes extrapolate exactly how big that image should be. So it's always cool to see this working in real life. Okay? You can also think of it in terms of kind of the fact that you can focus light rays with a magnifying glass, and you can that's actually a convergence of the light rays, and burn things, like burn a hole in the paper with that idea. So always try to relate it to real life things. Okay? So you know what's going on. Okay, so now we have a diverging lens. Oh, okay. So in accordance with our rules, what type of image are we going to have no matter where we put the object when it comes to your diverging lens? Good. Just think about that security mirror. So it makes all the images smaller. They're virtual, okay? And you know that they are in fact going to be upright. So don't worry about the individual diagrams. So worry about what's going to be the result of this idea. Okay? And you can take a screenshot of this if you'd like. So diverging lens, this is what we see. Okay. So if we think about this idea, we said the object between C and F, behind the focal point. Okay, well, you've already told me this. You know what? You can teach this lesson from now on in. Behind the focal point, remind me? So behind the rim. Monique was like, okay, it's going to be real, inverted, and it's going to be magnified. Object at F, we know it's going to be no image, regardless of it's a lens or a mirror. If it's in front of the focal point, we know that we want it to move in front. So it's going to be magnified, it's going to be upright, and it's going to be virtual. And when it comes to the concave lens, we know that the concave lens, remind me, what's going on with the concave lens? Okay, it's going to be reduced, it's going to be upright, and it's going to be virtual. So that knowledge by itself will get you through a lot of the questions that you'll see on the MCAT. So I'm really glad that you're picking that up and putting it together. And if you want to take a screenshot of this, you can. Okay. So with that, we can answer this question. We want to know the path of this emerging ray. Okay. Awesome. I'm glad, Alyssa and Lauren. So it enters a piece of glass. The piece of glass has a higher value of n. So since it has a higher value of n, should the light ray move towards the normal or away from the normal, since we have a higher value of n? It should have been towards the normal. Okay? So we look at this, and we're like, answer choices that aren't bending towards the normal, like B and D, we want nothing to do with you because it's coming in, has a higher value of N, we don't want to see you, goodbye. Okay, so it should have been towards the normal. And then if we take a look at that idea, we say to ourselves, well, if we're thinking about what we are going to be dealing with, let me get rid of this idea, we say, okay, well, we then can say, well, based upon what we have next, we then can figure out, well, as it goes back into the air, what should happen to the light ray? Should it bend away or should it bend towards the normal? As it goes back into the air and it can more easily travel, it should bend away. Okay, so that's how we know that our correct answer choice is indeed going to be A. So remember that. The more dense the material is, the more it's going to bend the light ray towards the normal. So glass is denser than air, so the light going into glass is going to bend it more towards the normal. The less dense that the material is, the light rays are going to bend away from the normal. So that's how we get air towards the normal for glass, and then back away from the normal back to air. Okay? Just like that, you got the correct answer. You know what's going on. Okay? So good deal there. So now let's take a look at our learning goal 3, and we'll take a look at diffraction and what you need to know about that for test day. So we deliberately aren't going to spend a lot of time on this because it's not as important for some of the topics that you'll need to see on test day. But we do have the idea of the light rays spreading as they are going to be going through a slit or as they're going to be going through a prism. And this is exactly what you see here, that white light will spread out into the rainbow. So here we have the idea of what happens when it's going through a single slit. So here you have the single slit, and you'll note that the light rays are going to diffract as it goes through a single slit. Okay? So you can see here we have the distance, the aperture of the slit. So it's going to be 1.5 angstroms that we have here. Okay? And the light rays are going to spread. And you'll see that diffracted wave as it goes through that slit. Okay. So then, if we take a look at a single slit, and then we send it through a lens, we have an equation that we can utilize for that. Yes. And if you want to take a screenshot of this, you can. Okay. And by the way, these aren't going to be particularly high yield, so just keep that in mind. We just want to kind of introduce you to the idea. So if you have a slit and a lens, you can use this equation in order to see what's going to happen. So you're going to have some diffraction, but then it's also going to go through the lens in the manners that we've described previously. And you'll see when you have the light rays that are going to be converging and the light rays that are going to be diverging. So when they come together, you're going to end up with a dark, with a bright fringe. When they're going to be interfering with one another, then you'll end up with a dark fringe. Okay? So when they're going to be actively additive to one another, bright. When they're interfering, dark. So we can actually visualize that idea when it comes to Young's double slit experiment, where you had multiple slits, and then you had the diffraction of these particular waves. So when you had the diffraction of these waves, you ended up with the light and the dark fringes. So right here, we have that positive interference. where it's additive and we have a whole bunch of light. Where it's a dark fringe, we know that we have that negative interference, where the light waves are going to be canceling one another out. Okay, so that's going to be something that you're required to understand. Positive interference, brighter light. Negative interference, they cancel each other out. So if you think about that, you can also apply this equation to that idea. But this isn't high yields. You really won't see it a lot when it comes to test day. But we just wanted to introduce this idea to you. So if you want to take a screenshot of this, you definitely can. Okay. So with that, we can figure out what's going to happen in this particular case. So if an object is moved from 2F towards F, okay, so we're getting closer to the lens that we have here. The image formed on the other side of the lens. We want to know where exactly that image is indeed going to be formed. So then we can look at it and we can say, okay, well, if we take a look at putting this in terms of equation form, we can think of it in terms of 1 over F is equal to 1 over I plus your 1 over O that you are looking at. So you say, okay, well, based on this idea, we're figuring out for the object at F what we want to happen to it. So we say, okay, we know that 1 over F minus our 1 over F is going to be equal to 0. And we know that we are going to get the image that we're looking at, because we're solving for I, is going to be at our infinity. So it's going to be from 2F to infinity. Okay, but don't worry too much about this question, because you won't see questions like this a lot on test day. Primarily what you're going to see is questions like we saw previously on the mirrors and on the lenses. So that's what you really, really want to focus on. Okay, and like I said, you can always come back and rewatch this lesson whenever you need to rewatch this lesson. So you figure out what happens to the object at F, and you figure out what happens to the object at 2F. Okay, to the image at F and the image at 2F. So with that, we have talked about the electromagnetic spectrum, we've talked about the ray diagrams, we've talked about the idea of reflection versus refraction, and we talked about some of the lower yield topics of your single versus your multiple slits and Young's double slit experiment. So hopefully you've gotten a huge insight into what's going on for the ray diagrams and your reflection, which is primarily what you're going to be tested on for test day. So thank you very much for attending this session. On behalf of Sonali and our wonderful Liz and our wonderful Chris, we thank you very much for attending, and we hope to see you again in another channel session. Have a great rest of your Saturday. Bye.